All right, welcome to the deep dive. Today we're going deep, and I mean deep, into something called the ergodic hierarchy.
Ooh, sounds intense.
It is, but fascinating, especially for someone like you who thinks about order, chaos, randomness.
You know me too well. Hit me with it.
Think of it like this. We're dissecting randomness, but within systems that actually have strict rules, deterministic laws. It's about the shades of unpredictability, you know.
Shades. So not just random or not random.
Exactly. And that's where this hierarchy comes in. It has 5 levels, like stepping stones. Ergodicity is the base level, then weak mixing, strong mixing, Kolmogorov, sometimes called K, and at the top, Bernoulli.
Okay, 5 levels, got it. But why a hierarchy? What's so special about the order?
It's nested, meaning if something's Bernoulli, it's automatically all the others too. Like a set of Russian dolls, the bigger one contains all the smaller ones.
Ah, I see. So Bernoulli's the most random, and as you go down, it gets less so. But each level implies the ones below it.
Nailed it. And our mission in this deep dive is to unpack each level, not just the definition, but what it means for how we see the world. We're talking statistical mechanics, the very definition of randomness, even how we describe chaos, all from a philosopher's viewpoint.
Now you're talking. This is why I love these deep dives. Let's get into it.
Right on. But before we climb that hierarchy, we got to start with the foundation. The ergodic hierarchy is all about dynamical systems. You familiar with that term?
Vaguely. It rings a bell, but maybe you should refresh my memory a bit.
No problem. Simply put, it's a mathematical way to describe how things change over time. Like a set of rules saying, if the system is here now, it'll be there later.
So like a recipe for change?
Perfect analogy.
Yeah.
And the source uses a great example, and really visual. A lead ball on a spring, you pull it down, let go, it bounces. A classic.
Simple enough, but how do you mathematically represent all the ways that thing can bounce?
Enter phase space.
Right.
Imagine an abstract space, and each point in that space represents one specific state of our ball and spring. Its position, how fast it's moving at that instant.
So like a snapshot of the system frozen in time, but every possible snapshot gets its own point in this space.
You got it. And as our ball bounces up and down, that point moves in phase space, tracing a path. That path's called a trajectory.
A history of the system's movement through all its possibilities, kind of like a map of all potential destinies for the ball.
Precisely. Now, imagine tons of these trajectories, right? The whole phase space buzzing with movement. We need a way to say how big different sets of those possible states are.
Okay, so not just one ball bouncing, but maybe a bunch of balls with different starting points, all tracing their paths.
That's it. And that's where measure comes in. It's like assigning a size to regions in this phase space, like length, area, volume, but in this abstract space of possibilities. The key one is the Lebesgue measure, which is basically our normal ideas of size, but, mathematically rigorous.
Makes sense. So we got the space of possibilities, a way to measure how much possibility is in different regions, and the rules of how systems move through it all.
Bingo. And that, my friend, is an abstract dynamical system. It's formally written as a trio. X, dtx is the phase space, is the measure, and t tells you how things change over time.
TT. So that T is time, right?
Exactly. And it can be continuous, like time flowing smoothly for our spring, or discrete, like if we only check on a population every year. For simplicity, the source focuses on discrete time.
So it just jumps from one moment to the next instead of smoothly flowing. Easier to handle, I guess.
Way easier. Now, there's this crucial idea of measure-preserving transformations. This is key for philosophers like us.
Oh, I love it when math gets philosophical. Spill the beans.
Imagine a blob of states in phase space, right? As our system evolves, that blob might morph, stretch, fold, but its size, according to our measure, stays the same. No new possibility is created or destroyed.
Deep. So determinism means the possibilities are fixed, even as the system dances around within them.
Beautifully put. Now, to get to ergodicity, we need to talk about averages, but in 2 different ways. Time averages and space averages.
Averages. Huh. Haven't heard that word since, high school stats class.
Well, it's back with a vengeance. Imagine measuring, say, the temperature at a spot in a room over a whole day. The average of all those readings is a time average for that spot.
Makes sense. You're averaging over time, tracking how one thing changes.
Right. In our system, we'd take a function, like the energy of the system, and average its value as the system follows its trajectory. But here's the kicker. That time average depends on where you start in phase space. Different starting point, different average.
Okay, so time average is like a personal average specific to the trajectory.
Precisely. Now, space average is different. Imagine measuring the temperature at every point in the room at one instant. The average of all those is the space average.
So it's not about how one point changes over time, but about the whole space at one moment.
Exactly. And in our system, it'd be averaging the function's value across all of phase space, weighted by our measure. It doesn't care about any specific trajectory. It's an average over all possibilities at once.
Ah, I see. Time average is history dependent. Space average is about the whole landscape of possibilities.
Now you're getting it. And for us philosophers, this ties into probability. Space average is like the inherent likelihood of things, not based on any one system's history.
Mind blown. Okay, so much buildup. What's this ergodicity thing already?
All right, here it is. A system is ergodic if, for almost any starting point, its infinite time average matches the space average.
Almost any. That almost seems important for a philosopher. Like, what are the exceptions?
It's about sets of measure zero. Think of a point on a line. It has zero length, right? In a 2D plane, a line has zero area. They're there, but their size in the relevant way is nothing.
So those exceptional points where it doesn't match, they're almost nowhere in the grand scheme of possibilities.
Precisely. And philosophically, it means for almost all initial conditions, the long-term behavior mirrors the overall average properties of the phase space. The individual reflects the totality, given enough time.
That's deep. It's like saying, despite all the possible paths, in the long run, they all kind of experience the same average reality.
And the source gives another cool way to see it. Imagine a region, call it A, in phase space. If the system's ergodic, the proportion of time it spends in A over infinite time equals the measure of A relative to the whole phase space.
So if A is 1/3 of the phase space, you spend 1/3 of eternity there, no matter where you almost started.
Exactly. It's like democratic exploration. Every part gets its due, proportionate to its size and possibility.
I like it. It's fair. Now, the source mentions metrically indecomposable. That sounds intimidating.
It's a mouthful, but the idea is simple. You can't chop the phase space into separate pieces where the system gets stuck in one and never leaves. It's all interconnected.
So no walled-off gardens in phase space. Everything eventually leads everywhere else.
And that interconnectedness, that's basically equivalent to ergodicity. They imply each other.
Nice. Now, there's some math about limits and intersections of sets. I'm getting a bit lost there, honestly.
Yeah, that's getting into the weeds. The point is, it formalizes how regions mix over time in a way that reflects their size. Like how much of one region ends up overlapping another after a long time.
Okay, so it's about how possibilities blend together, not just whether they explore the whole space, but how they do it.
You got it. And that sets the stage for stronger forms of mixing, leading to what we think of as randomness. But ergodicity is the baseline.
Right, the first rung on the ladder. And I'm guessing it's not the last.
Nope, we're just getting started. Remember the whole ergodic hierarchy. It's about increasingly stronger conditions, each implying a deeper kind of randomness or unpredictability.
Like levels of chaos, each one more chaotic than the last.
You can see it that way. Bernoulli at the top, then Kolmogorov, strong mixing, weak mixing, and ergodicity at the bottom. Like we said, higher levels imply the lower ones, but not the other way around.
Got it. So Bernoulli's the wildest, and as you go down, it gets tamer, but never violates the rules of the level below.
You're a natural at this. Okay, let's climb to the next level. Mixing. And the source gets really down to earth here. They talk about stirring scotch into water.
My kind example. I'm all ears.
It's Gibbs's classic illustration. You start with scotch and water separate, then stir. The scotch swirls, stretches, mixes. Eventually, it's uniformly spread throughout the water, right?
Makes sense. A nice, even mix. Any sip tastes the same.
And strong mixing is the mathematical version of that. Imagine two regions in phase space, like blobs of states. As time goes to infinity, they become independent in terms of their measure.
Independent, meaning knowing where one blob is tells you nothing about the other. Like, if you find scotch in one sip, it doesn't mean the next sip will be all water.
Precisely. The math says the amount of one region that ends up overlapping another after a very long time is just proportional to their sizes, no matter how they started out.
So no matter where you look in the glass, you find the same proportion of scotch. It's perfectly mixed.
Now, weak mixing is a bit more relaxed. Instead of that perfect mix always happening, it only has to happen on average over time.
So you might get lucky and have a strong scotch sip than a weak one, but over many sips, it averages out to the overall mix.
Exactly. There can be temporary fluctuations, but in the long run, they smooth out. The math allows for these wobbles as long as they average to zero.
Interesting. So strong mixing is like a strict bartender, perfect proportions every time, while weak mixing is more, hey, close enough, you'll get your scotch eventually.
Love it. And the hierarchy holds. Strong mixing implies weak mixing, because a perfect mix is always going to average out right. But weak mixing doesn't mean it's always perfectly mixed.
And both of these imply ergodicity, since they're exploring the whole space anyway. But just wandering around ergodically doesn't guarantee you're mixing things up well.
You've mastered the concepts. Now we go up to Kolmogorov systems, or K systems for short. And here, the math gets really abstract.
Oh boy, here we go. Brace yourself for some philosophical head-scratching.
The source even says the standard definition is tough to grasp intuitively. It talks about K-mixing and supremum over a sigma algebra. Heavy stuff.
My brain's already hurting. Can we get the Philosopher's Digest version, please?
Essentially, K-systems have such strong unpredictability that the distant past becomes irrelevant to the future. Like it loses its memory so thoroughly that it doesn't matter how it got there.
Whoa, that's a powerful kind of forgetting. So even if we knew its entire history, we couldn't predict much about the future.
That's the idea. And they link it to something called Kolmogorov-Sinai, KS, entropy, which, entropy usually means disorder or randomness.
Right, like how much messiness there is. So more entropy, more randomness, less predictability.
You got it. And KS entropy, despite all the fancy math behind it, has some super insightful interpretations. Firstly, it connects to positive Lyapunov exponents.
Exponents, like those things that make numbers grow really fast.
Exactly. And in this context, they describe how fast nearby trajectories diverge. Positive exponents mean they separate exponentially, a hallmark of chaotic systems.
Ah, the butterfly effect. Tiny change now, huge difference later.
Exactly. And Pessin's theorem formalizes this link between K-systems and these exponents. So even tiny uncertainties in the present get amplified wildly over time.
Wow, so even with perfect knowledge, you can't predict the future because any tiny error explodes. Deterministic, but unpredictable.
Mind-blowing, right? But wait, there's more. KS entropy also connects to algorithmic complexity. It says the shortest computer program to reproduce the system's trajectory is really long.
So not only is it unpredictable, but it's complex in a fundamental way. No simple pattern underneath it all.
Bingo. Brudenau's theorem says that's what K-systems are like. The randomness isn't just lack of knowledge, it's inherently hard to describe.
Okay, now that's messing with my definition of randomness. Not just what we don't know, but something deeply complex in the way it unfolds.
And lastly, KS entropy relates to Shannon entropy, which is all about information theory. Basically, high KS entropy means the system constantly generates new information, making the future more uncertain.
So not only can't we predict it perfectly, but it keeps throwing new curveballs at us, constantly adding uncertainty. That's a wild system.
Wild indeed. Okay, ready for the summit. We've reached Bernoulli systems, the kings of this hierarchy.
Bring on the ultimate randomness.
To get there, we need to talk about partitions. Imagine cutting our phase space, the whole space of possibilities, into non-overlapping pieces that cover everything.
Like slicing a cake. Each slice is separate, but together they make the whole cake.
Perfect analogy. And two partitions are independent if knowing which piece you're in from one tells you nothing about the other. Like knowing you're in the chocolate slice doesn't tell you if you're in the left or right half of the cake.
Zero information gained. Okay, so how does this cake slicing lead to Bernoulli?
A Bernoulli system has a special partition. It's Bernoulli partition, where the pieces stay independent even as the system evolves. Like, no matter how you slice the cake initially, after shuffling it around, knowing which piece you're in at one time tells you nothing about where you were or will be at any other time.
So it's like each moment is a totally fresh coin flip, completely unrelated to the past or future. Pure randomness, even though it's following deterministic rules.
You nailed it. It's like an endless sequence of independent coin flips, the ultimate unpredictability within determinism.
I'm starting to see why this stuff is so mind-bending for philosophers. Okay, source mentioned Baker's transformation. Is that another analogy?
It is. Imagine a square of dough. You stretch it out, then fold it over. Repeat that over and over. Turns out that has a natural partition into left and right halves, and those stay independent over time.
So no matter how much you stretch and fold, knowing which half you're in now tells you nothing about where you'll be later.
Exactly, and the source gets even deeper, saying this relates to shift maps by looking at the coordinates in binary. Like the transformation is just shifting bits around, similar to flipping a coin repeatedly.
Whoa, that's a whole other rabbit hole. So Bernoulli systems are like the epitome of random-like behavior, even though they're deterministic underneath.
You got it. The source also mentions weak Bernoulli and very weak Bernoulli, but those are technical details for proving certain transformations are Bernoulli in a deeper sense.
Okay, I think my brain needs a break from abstract randomness for a bit. Let's get back to the real world. The source talks a lot about statistical mechanics. Why is this ergodic hierarchy so important there?
Great question. Statistical mechanics tries to bridge the gap between the microscopic world, like atoms bouncing around, and the macroscopic world, like temperature and pressure. And ergodicity is key, especially in the Boltzmannian approach.
Okay, reminder. Boltzmann's the one who said entropy always increases, right? Like your room always gets messier unless you put in effort.
Exactly. And his view is all about how systems evolve in phase space. Imagine the phase space of a gas, all those molecules zipping around. Macroscopic states, like the gas having a certain temperature, correspond to big regions in that phase space.
So like all the different ways the molecules can move while still giving the same overall temperature.
Exactly. And Boltzmann entropy is about the size of those regions. His idea is systems tend towards equilibrium, the highest entropy states, because those regions are the biggest, so the system spends most of its time there.
Makes sense. If most of the phase space corresponds to one temperature, the system's going to spend most of its time at that temperature.
And that's where ergodicity comes in. Boltzmann hoped that if a system's ergodic, it visits all regions proportionally to their size, justifying the idea that the probability of a macrostate is basically its volume in phase space.
So if equilibrium's the biggest region, it's also the most likely because the system spends most of its time there wandering around ergodically.
Exactly. But there are problems with this reliance on ergodicity. For one, proving it for realistic systems is super hard. We have some results for simple models, but nothing general.
So we're kind of assuming things are ergodic without really knowing for sure. Not very satisfying for a philosopher.
And there's more. Some systems act thermodynamically. They reach equilibrium, even though they're not ergodic, like the Calic ring model, or systems of uncoupled oscillators.
So ergodicity might not be the whole story for how systems reach equilibrium. There might be other mechanisms at play.
Precisely. And the source goes into various responses to these objections, like almost ergodicity or the ergodic decomposition theorem.
So folks are trying to salvage the connection, but it's messy. It's philosophy of science at its best, trying to make sense of the foundations when things get complicated.
And we can't forget the measure zero problem. Those tiny exceptions, the sets of measure zero where ergodicity might not hold. Philosophically, they're troubling. What if some crucial behavior is hiding in those negligible regions?
Yeah, just because something's mathematically small doesn't mean it's unimportant for understanding the world. Size isn't everything.
And then there's Albert's critique. He argues ergodicity is basically irrelevant for the arrow of time and equilibrium, emphasizing the past hypothesis and transition probabilities. It's a whole different way of looking at things.
So the relationship between ergodicity and the Boltzmannian view is, shall we say, complicated. What about the Gibbsian side of things?
Good point. Gibbs focuses on ensembles, which are imaginary collections of tons of copies of the system, all in different states. Instead of one trajectory, you have a probability distribution over all possibilities.
So instead of one ball bouncing, you have a cloud of possibilities with different densities in different areas.
You got it. And averages in Gibbs are ensemble averages, calculated over that whole cloud. Gibbs entropy is defined for that distribution, and there's this maximum entropy principle for picking the right distribution at equilibrium.
Sounds powerful, but how does this cloud of imaginary systems relate to the one real system we're actually observing?
That's the philosophical puzzle. The textbook justification usually says, well, if the real system's ergodic, its long-term time average should match the ensemble average. But that's assuming a lot.
Like assuming we can actually measure for an infinite time, and that our finite measurements accurately reflect that infinity.
A bit of a leap of faith, right? Exactly. And there are other attempts to connect ensembles in real systems, like Malamud and Zabel's work. And the idea of epsilon ergodicity suggests maybe ergodicity just needs to hold for a really big chunk of the phase space, not perfectly everywhere.
So people are trying to make it work, but it's still tricky. And then there's Kinchin's stuff about systems with many degrees of freedom. He showed some convergence between time and space averages, but it's limited to specific types of systems. And the thermodynamic limit program is trying to generalize that further.
Right. It's an ongoing area of research. And in Gibbs, there's also the problem that Gibbs entropy stays constant over time. That seems to contradict the second law of thermodynamics, where entropy always increases.
Right, things get messier, not stay at the same level of messy.
People try to fix this with coarse graining, defining a coarse-grained entropy that can increase. But that depends on mixing and introduces subjectivity, so it's debatable.
So long story short, both Boltzmann and Gibbs rely on ergodic ideas, but it's a tangled web. The relationship is complex and full of open questions.
Couldn't have said it better myself. Now let's shift gears to something even more fundamental. Randomness itself. The source says the ergodic hierarchy, though it doesn't explicitly mention randomness, is often seen as a hierarchy of increasing randomness in deterministic systems.
So like more ergodic, more random, but how do you measure randomness if it's all following fixed rules?
Right, that's the puzzle. And these philosophers, Berkovits, Frigg, and Kranz, they connected to unpredictability. They say randomness is about how much past information is relevant for predicting the future.
Makes sense. If the past doesn't tell you anything about the future, it feels more random. Like if coin flips were somehow connected to past flips, it wouldn't feel truly random.
Exactly. And they bring in probability. They define an event as the system having a certain property, which means being in a certain region of phase space. And they have this probability postulate, linking the probability of an event to the size of that region according to the measure.
So bigger region in phase space means higher probability. Makes sense.
And here's the key. They show that how relevant a past event is for predicting a future one is mathematically the same as the correlation between the corresponding regions in phase space after taking time evolution into account.
Whoa, so my subjective feeling of knowing the past helps me predict the future is tied to this objective mathematical correlation between sets in phase space. That's deep.
And that lets them rephrase the whole ergodic hierarchy in terms of these correlations. Bernoulli systems, those independent coin flips, have zero correlation between past and future. K-mixing means correlations with the distant past vanish. Strong mixing means correlations fade away as time passes. Weak mixing just means they average out to zero but can still be there. And ergodicity, well, it doesn't guarantee anything about correlations.
So it's not just about exploring the space, but about how much the past whispers to the future. Bernoulli's totally silent. K-mixing forgets the distant past. Strong mixing gradually loses the signal. Weak mixing just hears static. And ergodicity, well, it might be listening to anything.
Beautiful analogy. So this framework gives us a way to see ergodicity and its stronger cousins as levels of unpredictability based on how much the past hangs around in the present. Bernoulli's the ultimate forgetfulness, and thus the most random in this sense.
I'm liking this. It's giving me a whole new way to think about randomness, not just as chance, but as this fading echo of the past. Okay, but the source mentions a common criticism. Most real systems aren't ergodic.
Right, we touched upon that with statistical mechanics.
Yeah.
And it's a valid point. But the source counters by saying, firstly, there are ergodic systems out there, like those hard balls bouncing around. Maybe not everything, but it's not just a theoretical fantasy.
Fair enough. At least it exists somewhere.
And secondly, even if the whole system isn't ergodic, there might be parts of its phase space that are. Like Cam theory says, some regions can be stable and predictable, while others go wild and might be mixing or even Bernoulli.
So it's like a landscape with calm lakes and raging rivers. Not everything's chaotic, but chaos exists within the overall structure.
A perfect analogy. And the source reminds us that even though those ergodic definitions use infinite time limits, they still have meaning for finite times. It's all about limits approaching something. Like if it's mixing, the correlations will eventually become negligible after some perhaps long but finite time.
Okay, so it's not useless just because we can't actually measure forever. There are real-world consequences, even if we can't reach true infinity.
Exactly. And one last thing. The hierarchy isn't about a strict ranking of how fast correlations decay. It's more about the kind of decay, the quality of the forgetting.
Makes sense. It's not a race to zero correlation, but about how that process happens, what kind of information gets lost along the way.
Okay, one final topic, and this is a big one. Chaos. It's notoriously hard to define. Does the ergodic hierarchy help us here?
Chaos. It's like I know it when I see it, but putting it into words is tough. So is ergodicity chaotic?
That's the debate. Some say strong mixing is necessary for chaos, while being a K-system is enough. The idea is K-systems have those positive Lyapunov exponents, the butterfly effect, and positive Ks entropy, all signs of chaos.
Makes sense. Those things make a system seem really chaotic, but the source says it's not that simple.
Right. Strong mixing doesn't always mean exponential divergence. It could be slower. And sometimes, even slow divergence can be more dramatic than exponential in the short run.
So judging chaos by how fast things separate might be misleading. It's more nuanced than that.
And chaos entropy, while linked to chaos, might not be the perfect dividing line either. Some argue that strong mixing, even in dissipative systems, is the real key because of things like sensitivity to initial conditions and dense periodic orbits.
So lots of back and forth, no easy answers. And the source even says maybe chaos isn't all or nothing, but a matter of degree along the hierarchy.
Yet, Bernoulli's systems are like maximum chaos, with total independence. Ergodic systems might be non-chaotic, since they don't even guarantee decay of correlations, and everything in between is somewhere on that spectrum.
So the ergodic hierarchy gives us a framework, not a strict definition. It helps us dissect chaos, understand its different facets.
And the source even mentions it's used to study quantum chaos and model errors. Its reach goes beyond just classical systems.
Okay, so much to think about. What a deep dive this has been. We went from bouncing balls to abstract spaces, from scotch mixing to the very nature of randomness and chaos.
And we did it all from a philosopher's perspective, questioning assumptions, connecting concepts, and pushing the boundaries of how we understand the world.
Exactly. And we saw how the ergodic hierarchy, while not a perfect tool, gives us a way to analyze unpredictability, the fading influence of the past, and the emergence of randomness from deterministic laws.
And it all ties back to those big philosophical questions about determinism, free will, even the nature of knowledge itself. If even systems with fixed rules can be so unpredictable, what does that say about our own place in the universe?
Deep stuff. I'm going to need some time to process all this.
Me too. But that's the beauty of it. It's not about easy answers, but about opening our minds to new ways of thinking about fundamental concepts.
Couldn't agree more. And to our listeners out there, I encourage you to ponder this. Does math give us the true measure of randomness? Or is it always colored by our human perspective, our need to understand and predict?
A perfect ending note. It's not just about the math, but about how we interpret it, the philosophical lens we bring to these questions. Thanks for joining us on this mind-bending journey. Until next time, keep diving deep.